Okay, good afternoon and welcome back faculty members, teachers. This is the second class of the CNC. First class we had discussed about the industrial revolutions, how from the very first generation machine tool, how we have landed to the state of the art industry 4.0 machine tool, that is CPMT, cyber physical machine tool. That was our last slide of the first lecture. Okay, in the last class we had discussed about the basics of LC CNC, what are the key feature, key components, advantage and limitations of the LC machines, and when in 1970s computer came into existence, all LCs were converted to the and upgraded to the computer numerical control system, and due to presence of computer, lot of added advantage can be accrued, that we had discussed. And of course the three major components of the LC machines, one is program input device. The main thing that the heart or the brain of the machine is machine control unit, and third is the machine tool unit, which is almost looks like our conventional machine tool, but some modifications are there as regard to the guideways modifications and major modification in the replacement of the recirculating your conventional leads to by recirculating balls to for improving the transmission efficiency. So that link will be available in our next week. Today we will discuss the very details of NC and CNC machine tools. So chronologically we will consider axis nomenclature, classifications based on the positioning system, the detailed block diagram of the CNC machine tool. Earlier in the first class what you had discussed about the block diagram, as I mentioned that there were three major components, but today the same thing will be explored in a larger perspective, so the details of the entire block diagram of the components would be visible to us. This is a approach to programming. There are two different approaches available for the programming. One is absolute mode, another is incremental mode of programming, and both have got their relative advantages and disadvantages that we will discuss. And most importantly we will discuss the open loop and closed loop system control, and this servo control loop, which is the last one, that is basically augmentation of the basic closed loop control system. Okay, so one after another we will discuss. So let us first start with axis nomenclature of NC CNC machine systems. In the first class I had told you that this NC or CNC machine tool is supposed to work in an unmanned mode. So there will be a part program which is in the form of coded instruction, which comprises basically some alphabets and numeric, and of course in some cases there may be some relational operators like symbols may be present, but predominantly it consists of alphabets and numerics. As regard to the positions, we have to rely, or the system relies on coordinate geometry. So okay, so if it is a coordinate geometry system, so our first role will be to identify the axis nomenclature, which will be the x-axis, which will be the y-axis, and which will be the z-axis. So this x, y, z is according to the linear movement, but additionally there is a possibility of having rotational movement. Those are identified as A, B, C. So anyway, let us start about the Cartesian coordinate system. The most important coordinate in case of NC CNC machine is z-axis. So that is why you have started with the z-axis first. Whether it is lathe categorically machine or milling categorically machine, first the most important axis is the z-axis. Which one will be the z-axis? It is the horizontal or the vertical, that is not the important. Z-axis will be identified always along the spindle. If you think about the lathe, so the sharp job is clamped and given a rotational motion. Okay, so along the chart, that rotational motion along the bedways, longitudinal direction, that is identified as z-axis. In case of milling and drilling, if you think about the spindle is remain vertical, then the cutting tool, whether it is drill bit or a milling cutter, that is mounted in the vertical position. So apart from its rotation, it keeps on moving up and down. Okay, so in that case this will be the z-axis, the vertical will be the z-axis. Okay, now regarding plus and minus, that is very important. Z minus is such a direction which will bring the tool or the job or both, if you consider, closer to each other. If you consider the job is stationary and tool is moving, so Z minus direction will be that particular movement or in that particular direction such that distance between the tool and job is keep on decreasing. Suppose vertically the job is something like this. Okay, it is kept on a vice, say on a drilling machine. The drill bit is mounted on the spindle, it keeps on rotating. So leave aside the rotation. But as regard to the drilling operation, it will keep on coming down while taking a cart. So in this particular direction, when it is coming down, you just mark it, notice it. The distance between the tool and the job keeps on increasing or decreasing? Decreasing. So this will be Z of minus. So downward movement will be identified as Z minus. If we take the example of a lathe, in a chuck, job will be clamped like this way. It will keep on rotating, tool will be positioned somewhere else. So during cutting, the tool will come closer to the job. So movement towards the left will be Z minus. So this is Z. But regard to minus plus, when it comes closer to the job, it is Z minus. When it is going away from the job, it is Z plus. Similarly, in case of drilling or milling, when it goes up, the distance between the tool and job increases. So that is Z plus. Okay. So that is the first. Second is the x-axis. In lathe, it is the direction of the cross axis. If you take the example of this threaded pin, it will be clamped in the chuck, it will keep on rotating. So the tool which is mounted on the tool post will have two motions. One is longitudinally, that will be along the axis, which we have already identified as Z, and as regard to the radial movement or crosswise movement, that crosswise movement is identified or captured by the x-axis. Again, coming to minus or plus, when it takes the depth of cut so that the tool approaches toward the center or moving toward the center, that means again the logic remains same or the convention remains same. The distance between the tool and job keeps on decreasing. I am moving toward the center as if it is my fingertip is the tool. So if I move toward this way, what will happen? The distance between the tool and job keeps on decreasing. So this is x minus. As we withdraw the tool from the job, x plus. Okay. Importantly, in case of CNC lathe or turning center, mind that there is no y-axis. Okay. Why it is so? Again, just imagine a conventional lathe also. The tool can have only two movements. One is longitudinally and another is crosswise. Okay. So in any direction, if we apply some amount of depth of cut and since the job is revolving, so eventually it will generate a circular surface. So if you put the depth or apply the depth of cut from any radial direction, it will have an uniform or the same effect. That is why any third axis, that is y-axis, is not required. If you consider, it will be determinant. Have you got this point? Suppose this is a circle of 15 mm diameter. If I give a depth of cut from this direction, any arbitrary direction, and if it keeps on rolling, what will happen? Job of smaller diameter will be generated, or circle of smaller diameter will be generated. So it is immaterial whether I apply depth from the lower side or from the right side or from the top side or from the left side or any angular side. Over the 360 degree it will have a same effect. So that is why only x-axis and z-axis is sufficient. There is no need of any establishing y-axis. Clear? But in case of drilling or milling, the job will be mounted on the table. Okay. Regarding the Z movement, it is on the spindle. Now from your side, just following the conventional or positive coordinate system. From your position, if you have given a graph paper, if you are told to draw a x and y axis, so x axis will be horizontally from left or from the origin towards the right, and as far as y axis is concerned, it is upward. the same logic holds true in case of milling machine and drilling machine. Okay, so usually the length of traverse, which is the largest one, that direction is identified as usually as x. Okay, as if you are sitting in front of a table, so this will be the that corner will be the your origin. So that will be the x-axis. This will be the y-axis. That is the y positive, x positive. Similar to our graph convention. Okay. So that is why I had categorically mentioned it is the remaining primary axis but not present in lathe. So this is how, whether it is drilling, whether it is milling, whether it is lathe, the rule remains same, logic remains same. Only thing, your orientation changes depending on the nature of construction of that particular machine. In case of lathe, chuck usually remains horizontal, but in case of drilling or milling, the spindle remains in the vertical position, although horizontal milling machine is also available. But in that case also we have to change our conventional system accordingly. But you cannot change that along the spindle I would like to define it as a y, that is not acceptable. That is why this axis nomenclature is important, and it has to be established and should be conversant with this system, because all the tool movement will be identified by its relative coordinate points in terms of x, y, z. Okay, so that is why it is imperative at the very beginning to identify and establish the axis nomenclature. Clear? This is just a axis nomenclature of a CNC lathe. Okay, it is not very prominent, but still it is visible. So you can see this is the chuck. Here the tool is mounted on the tool post. So this will be a longitudinal axis. So as the tool is moving towards right, z increases. That means gap increases. So this will be z plus. As it moving towards the approaching towards the job, it is z minus. Okay. Similarly, towards the center, x minus. Away from the center, it is x plus. It is another view. Okay, same thing. As if the job is clamped over in the chuck, this side there is a tailstock support. So as regard to this particular face, okay, so this will be z plus, this will be z minus. Okay, x plus, it is symbolized as if it is going up. That means away from, and x minus towards the center. Okay, so that is the convention. Same thing for the milling and drilling. See, the job is mounted on the table. This is the vertical spindle. So the spindle can go up and down. So this will be the Z, and as regard to plus or minus, as it comes down, the distance between the tool and job decreases or keeps on decreasing. So this downward movement is Z minus, upward Z plus, and x plus, x minus, y plus, y minus, similar to our conventional right hand coordinate. Clear? Additionally, to offer more flexibility in case of particularly the CNC milling, afterwards we will study in detail about the machining center, because predominantly real life machines or CNC machines either falls in the turning center category or in the machining center category. If you can recall the first lecture, I had shown you two colored photographs, one having the title turning center, another is machining center. Okay, afterwards we will discuss in detail, but turning center falls under the lathe category, while machining centers belong to milling category, with of course some added advantages. But the thing is that those machining centers similar to milling machine, so x, y and z axis are present. Additionally, if you have 5 axis machining center, then in addition to these 3 longitudinal or linear motion, 2 circular motions are also possible. That offers your range of flexibility to offer undertake machining of the complex jobs like gearbox. In one setup, what are the other 2 motion? Those 2 are rotary. One thing, it will allow the cutting tool, which is initially in the horizontal mode or horizontal position, it can swivel like something like that. Okay, so that is one additional rotary motion. Secondly, the job is mounted on the fixed table. This table can be swiveled also. It can be tilted. So 3 linear plus 2 rotary motion that gives rise to the concept of 5-axis motion. So anyway, generically, so you see x, y, z according to the your right hand rule, these are established. Additionally, along the 3 basic axes there are 3 rotary motion. Okay, rotation about x axis is identified as A, rotation about y is identified as B, and rotation about z is identified as C. So 3 linear plus 3 rotary, so maximum 6 degrees of freedom or 6 motions are possible. But in reality, 5-axis machining center is available in the industry, which offers lot of flexibility to undertake different wide varieties of jobs without go for any setting changes. Okay, this is vertical machining center. Since it is vertical machining center, so that is why z axis is vertical. That means spindle basically remains vertical. In case in the second one, horizontal machining center, in that case z axis you see the horizontal. That is why it is so named or so classified. Horizontal vertical means primarily your spindle will remain either horizontal if it is horizontal machining center, and it will occupy vertical position if it is vertical machining center. This is another way of classification. This is also extremely important for the tool path generation. Fundamentally, there are 2 categories of motion. All the tool path that can be broadly classified under the 2 broad categories. One is point to point, another is continuous. Point to point, the very name implies the tool movement from one point to the other point is important. The path along which it is moving, that is of no value. Suppose the tool occupies a particular position at this point, which is identified its xyz coordinates point, say x1, y1, z1. Then from this point, it is supposed to come to another point having its coordinate value x2, y2, z2. Now from this point to this point, it can follow any trajectory. It may be direct straight line, it may be circular one, it may be a zigzag one. So this intermediate path is not of significance. Only these 2 extreme points, restoration of these 2 extreme points is important. What would be the application? In which types of machining this accurate positioning rather than the path, that is important. Drilling. Just imagine a drilling operation, how a drilling operation is carried out. You have got a job, the drill center points are identified, so tool should move accurately to the, say in a particular job there are, suppose you see that there are 3 holes, so it is expected that these 3 holes should be drilled. So from any particular point, the drill bit should come to the center point of the first hole, but keeping a margin of some gap from the top of the job so that it will not collide initially. So the objective is to bring correctly the drill center point exactly above the coordinate of the first drill location. Once it reaches this particular point, then in the subsequent movement, it will, with a rotation and the feed, it will keep penetrating the job according to your desired depth. It will enter into the hole while moving, then it will be retracting by reversing its rotation, then it will go up. Okay, then if it is required in your second hole location, then from this first one it will move to the second hole center point, of course maintaining the some gap so that there will not be collision. So once it reaches the exactly or accurately the drill center point of the second hole, again it will be repeated as regard to drilling operation is considered. Then it will return back, again move to the third, so likewise it will keep on continuing. So how it is moving from in space from first point to the second point or second point to third point, that is immaterial. but correct position is important as regard to drilling operation is concerned. Okay, so in that case, point to point interpolation is important. So drilling is the one of the finest or very prominent application of the point to point system. In all other cases, the tool movement is continuous, whether it is milling, whether it is lathe, both all are basically continuous. If you carry out turning operation, the tool will move something like this way. You put the job in this way, it will keep on rotating. Tool will occupy a position something like that. So it keeps on rotating continuously, and tool movement will be along the Z axis with some amount of depth of cut. If you want to go for the facing, it will have a crosswise movement. You can have taper turning operation. You can have a profiling operation. So whatever be the operation, the tool movement is continuous. Okay. In case of milling, if you want to carry out all four sides milling, so the tool, while rotating, the tool is following this particular path. So movement is continuous. Okay. So one is point to point, another is continuous. Again, this continuous category can be further subdivided into another stage that is called paraxial and contouring. What is paraxial? The very name implies paraxial, means parallel to any axis. So again, returning back to lathe, if you undertake a turning operation, the tool movement is always along the Z axis, no X axis movement. So it is exclusively parallel along the or parallel to Z axis. If you undertake facing operation, no Z axis movement is there, movement is exclusively around X axis. So when it is either parallel to X or parallel to Y or parallel to Z, as the case may be, that is called paraxial. Okay, so two examples I have included, one is turning, another is facing. Similarly, if we would like to generate some typical contour, a particular profile, see, you see typical profiles are there. This is a semicircular path. So this particular trajectory I would like to generate in a CNC milling. That is a typical contour I am looking for. So that is called contouring. Okay. And fundamentally, all these motions are implemented through different types of interpolation. Those are called linear, circular, helical, cubic, parabolic. But out of these five, these two are very prominent and available in any category of CNC machines. These are very higher order and very sophisticated and usually not available in the CNC machines unless you pay for that and upgrade your system. I will explain still. Linear interpolation. Linear interpolation, one example would be your taper turning. Whenever you see, this is the turning is along exclusively along X, Z, facing exclusively along X. But whenever you are generating this taper path means tool will move something like this. That means it is a combination of X and Z, combinatorial movement. Or in case of milling, if we would like to generate a taper like this, you see that it is neither parallel to X nor parallel to Y. There is it is a combination of XY movement, a 45-degree path, maybe something like that. So that is your what is called linear. That means interpolation needs to be carried out in more than one axis, usually two. It may be XY, it may be XZ in case of lathe, XY in case of milling. Clear? So taper turning, this sort of profiling. Okay, these are the examples of linear interpolation. Now, if our interest, quite often it happens, the majority of our mechanical components that we use apparently seems very complicated, but if you decompose it into the fundamental geometrical entities, you will find the example of points, circles or arcs and line segments. Apparently it looks very complicated. But fundamentally, what are the items or geometrical entities available? One full circle. This is paraxial. This is paraxial. Here is also some arc. This is also parallel, and this is taper. If you want to carry out a hole at the center point, that is also possible. Anyway, it is not present in this particular job. So majority of our job apparently looks complex, but fundamentally it consists of fundamental geometrical entities like point, straight line, and circle. That is why this linear interpolation and circular interpolations are implemented, or systems are designed in such a way so that these two interpolation algorithms can be executed. Clear? Now, other higher order interpolation are helical, cubic, parabolic. How helical path can be generated? In horizontal two axes, there will be circular interpolation like this one. Now see, the depth of cut, depth of this hole or the ring is uniform in the z direction. That means having a 0.5 or 0.7 millimeter depth, entire circle is drawn or cut. Now in addition to this circular interpolation, if you move the cutter at the same time linearly in the other third axis, then you can have helical interpolation. Helix path, how it is generated? You just imagine a spring. You compress a spring, then you expand or open it. So you from the top you look like a circle, but along the vertical z axis it keeps on increasing along the length. So the entire path is something like this. So it is generating circular path in the horizontal plane, but at the same time there is a linear motion along the vertical axis. Okay, so two axis linear rotary or circular and one axis linear. These combinations will lead to the development of helical path. Now cubic and parabolic, these are very complicated and used in some specific cases for aerodynamics profiles, automotives, turbine blades. Those surfaces cannot be captured or cannot be represented by analytical equations. Just for a straight line, it can be represented by an equation A in the form of ax plus by plus c equal to 0, or for a circle x square plus y square equal to r square, something like that. But these surfaces are so complicated, these cannot be captured or represented by a single analytical functions. So in that case, higher order mathematics are required, and the most popular and efficient method is called parametric representation. I am not going to that much details of the mathematics. That is a part of your CAD, computer design, if you want to study more. So those analytical, I will not say analytical, those sometimes called they are free form surface. So these discussions are included within the part of computer aided design, and usually in the outside or beyond the scope of CNC. Still, I will say this cubic, parabolic, this sort of free form surfaces which are extremely difficult to generate, and even through higher order mathematics, those are basically approximation. Perfect shapes or the perfect locus of those surfaces is very difficult to capture by any single mathematical relationships or functions. Some examples that you can remember: Bezier curves, Naft surfaces, B-splines. These are some sort of very prominent surfaces which are generically called spline. And cubic and parabolic interpolation falls under that particular category. And if you want to generate shapes in this domain, you ought to install some sophisticated CAM package. So manual calculation, it is never possible. It is too tedious and too complex. It is almost next to impossible. Okay, so higher order sophisticated your softwares are required to calculate that particular part, and still I am reiterating that there will be only approximation to that. Okay. This is the block diagram of the inside of the CNC machine tool. What I was talking about in the last class, in that particular block diagram, I had broadly shown one is your program input, one is machine control unit, and another is the machine tool unit, without going to the details of the inside component. But this particular figure depicts or captures the functioning and other key components within the system. First, you see there is a input device. That means once you prepare the part program, it has to be transferred to the machine control unit for codification or conversion or decoding purpose, so that high level language can be converted to the machine language and for retrieval of information. Whatever we have written, that must be understood by the machine. So this conversion, which is popularly known as decoding, from high level language to the machine language, which is in the form of binary. It is a combination of 0, 1, which we have perhaps studied in your digital electronics to some extent. So that is, so anyway, so that requires some medium where the part program would be captured and would be transferred to the machine. If you have in the current days, you have got your pen drive, so you can write your part program in the laptop, take it in the pen drive, go to the CAD/CAM lab, transfer to the machine. Machine has got memory, so it can be downloaded very fast. So anyway, so some input device is required, or so the machine it has got a NC console through which, so the keyboard you can also input the data of the program. Okay. This is the machine control unit. This is the heart of your CNC or NC machine tool system. So all the intelligent function, that means information processing, which is presented in your part program, that will be interpreted. Arithmetic calculations or intermediate calculations, if are required, that will be taken care of by this machine control unit, and it will be implemented. Now within the machine control unit, see that there is a partition. Left hand side shows data processing unit. It is popularly identified by its acronym DPU, and the right hand one, that is control loop unit, which is called CLU. Okay, so this data processing unit is basically responsible for extraction of data, undertake different calculations, particularly the interpolation algorithm, and send the command or instruction to the control loop unit for its implementation in the hardware. And this will keep on continuing unless and until the entire command execution is not completed. So out of this DPU and CLU, there is a hierarchy. DPU at the top level, just like our brain. So in the first class I had told you that our decision making is taken care of by our brain, and accordingly we influence our environment through our manipulator, that is the hand. In this case also, decision is taken care of by the data processing unit, and for implementation or execution purpose, the information or the process information rather, these are transferred to the control loop unit for execution. Clear? Now we see motion data that comes from the control loop unit to the drive system. Okay, now this drive system goes to the machine tool. This is a picture of a milling machine. So once again, as regard to the XYZ movement, so XY movement will be implemented in the table, and Z movement, that is the up and down of the your tool or the spindle, that will be along the Z. So this drive system is responsible for imparting X and Y motion of the machine tool table. Okay, you see where from the arrow originates, from the control loop unit. So all the decision, that means information processing, that part is taken care of by the data processing unit. It sends the instruction to the CLU unit for further implementation. So DPU to CLU, CLU to machine tool. So DPU to CLU, this is internally, that's why it is enclosed within a single machine control unit. But this arrow, it starts from the C control loop unit. So the motion commands for the XY motion comes to the drive system from the control loop unit, and that is eventually fed to the machine tool table, where your two control loops or closed loop control systems are there. We'll come up to the later part regarding the control system, control loop, and the rotation of the spindle. Okay, that is coming to the vertical motor, which is responsible for imparting rotational motion of the spindle. See, the spindle is vertical in this case. This is the spindle where the tool will be mounted. Another thing, you see, there is written what is called miscellaneous function. Miscellaneous function is a part of programming. Right at this stage, you won't be able to understand the entire spectrum of the different codes, which is included in a part program, that are broadly categorized under the two different categories. One is called G codes, which is identified by the alphabet G, and another is identified by alphabet M to represent miscellaneous code. Rotation of the spindle, tool change, pull and on off, these are the secondary operations which are included or identified as a miscellaneous functions, and tool motions are popularly known as preparatory functions, for which G is used as a code. G followed by different number. According to the assigned number, it will have a different interpretation and action. G01, G00, G02, that we will explain in detail afterwards. But just for your understanding, this miscellaneous function implies that tool rotation command is coming to the spindle of the motor, which is responsible for imparting rotation to the spindle. Okay. Another feature is that you can see this yellow box, feedback device, that we will explain a little bit afterwards. Feedback means as the tool or the table starts moving, the instantaneous positions and velocities are recorded by some feedback devices, and those instantaneous data is fed to the data processing unit so as to calculate the error value and generate equivalent amount of command, so that continuously there will be monitoring and actuation, and this process will continue unless and until that particular command which is undergoing implementation is completed. To continuous monitoring the displacement and the velocity, which is essential, we will discuss in detail afterwards. This continuous monitoring of the position and the velocity are required, and that has to be fed to the control loop unit for taking any corrective action, so that eventually there won't be any error in the system. You see, the two parameters are there. One is position, another is velocity. Position means basically displacement. Tool is moving like this, or the table along with the job is moving like this. So there is a displacement along x. So instantaneous position, it has to be monitored if you want to ensure accuracy. And similarly, at what velocity the tool is moving or the table is moving, which is represented in our manufacturing fraternity by feet, millimeter per minute or millimeter per revolution. Eventually that can be converted to millimeter per minute as well. If you express feet in millimeter per revolution, and if it is multiplied by RPM, then it can be converted to linear displacement or the linear velocity, millimeter per minute. That is the standard unit in which it is expressed. So we ought to measure the displacement and the velocity both together. But one device, which is popularly known as sensors and transducer, cannot measure both two different parameters, for which two different feedback systems are there. One will measure the position, another will measure the velocity. Okay, very popular position measurement device is encoder. We will discuss in detail. Or there may be a linear scale based on the Moyer fringe pattern, and for velocity measurement, usually tacho generators are used. So two different circuits are there for position and the velocity measurement, and their instant or actual data or instantaneous data will be fed to the control loop unit, wherefrom it will be sent once again to the data processing unit for calculation, for the computation of the error signal. Error signal means reference minus actual. Reference will remain constant, but with the passage of time, actual keeps on changing. Suppose you are supposed to move from this point to a coffee shop which is at a 50-meter distance. Okay, so your reference value is 50 meter. But once you start moving, your one step, as if one step covers 1 meter. So 1 meter is executed. So 50 minus 1, 49 meter is still left. Second step you move ahead. So how much is covered? 2 meters. How much is left? 48. Third step, how much you have covered? See, how much is the left? 47. So this is what this difference is called error signal. And as we approach towards your destination, so when you reach to the coffee shop, so you will be covered by 50 millimeter. So your desired of the reference value was 50, actual value is 50, error will becomes 0. Then system stops working. So this is how the system was, but continuously. Clear? So that is the, and there is a display unit where this instantaneous XYZ motion you can see. Okay, so that will act as a facilitator to the operator or the programmer. Have a glimpse of the major components. One part program is definitely required. One program input device, which we have discussed in the last lecture in detail. Machine control unit we have already discussed. Drive systems, machine tool, and feedback devices. Now come to the another approach to classification based on the programming mode. There are two ways you can define the coordinates. One is absolute, another is incremental. What is absolute? It is similar to our conventional graph paper or coordinate system. You first affix your data, identify this is as a, from your side, this is x, this is y. So if you want to specify the coordinate of any particular point, say 40, 50, that means x along the x-axis is 40, this is 50. Say suppose this is the second point, maybe 80, 90. So this is 80, this is 90. Okay, so the what exactly policy or the strategy or convention that you are following with respect to a common reference, the values are provided along x or along y. This is absolute. That means your datum or reference will remain constant, will remain unchanged. But in case of incremental, first you define your origin and identify the first coordinate. Okay, while defining the second one, the first point becomes the origin. So in that case, you have to take the incremental distance, considering the plus and minus. So that is the incremental mode. Now we can argue why both are required. Both have got certain relative merits and demerits. For absolute programming, the major advantage is that suppose the machine you have got a 20 number of blocks to capture the or to represent the entire part program. In the fifth block, suppose there is a power cutoff takes place, or there is a tool breaker, so machining stops automatically. So in that case, suppose the tool is in that particular path, the tool is supposed to move from this point to this point. Now after making some progress, maybe some intermediate point, it stops, the machine stops. So how will you restore or how will carry out the remaining part? You have to bring back the tool at the beginning of this particular block and starts working. Okay. Now if you want to start working, so you have to go back to the starting position, the coordinate of which you have to remember. This is possible in the absolute mode because the origin remains unchanged. But this system will not work in case of incremental mode because it is a volatile. Your origin is volatile, keeps on changing. Initially your 0 point becomes the origin while defining the first point. When you want to define the second point, first point becomes the origin. When you define the third point, second point becomes the origin. Okay, so we have got a volatile origin. So in that case, once the tool starts moving from one point to other point, the memory location data is erased out. It is no longer available in the memory. That is why it is difficult to relocate the tool at the beginning of the particular block along which or in which your accident or interruption has occurred. In that case, if you follow the incremental mode, as I told as an example that your problem or interruption took place in the fifth block. In case of absolute, you can start from the beginning of the fifth block. But in case of incremental mode, you have to start from the block number 1. That means, but material has been already eliminated in the block number 1, 2, 3, 4 depending on your composition. So lot of idle time will be consumed in the incremental mode. Okay, so that is the deficiency of the absolute programming. In incremental programming, particularly in case of drilling type of operations, one added advantage is that it has got a self-checking feature. You identify the origin initially 0, 0, just take 3 points 1, 2, 3. Okay, so identify or put their coordinates following the incremental mode and assume that after completion of the last operation it will return back to the origin where from it has started its operation. That means form a closed path or closed loop. 0 to 1, 1 to 2, 2 to 3, then back to 0. So one loop is there. Now for all these movements 0 to 1, 1 to 2, 2 to 3, 3 to 0, you take the value of delta x, sigma of delta x, incremental delta x, considering plus and minus. If your all calculations are correct, then you can verify that your sigma delta x will be 0. Since eventually the start point and the end point are identical. Same logic holds true in case of y-axis as well as z-axis also. You can simply take one example and verify. So it has got a self-checking feature. If you undertake some computational error, that will be verified whenever you go for this sort of self-checking. Again, in the incremental programming, there is an added advantage. Quite often, your mechanical people deal with the jobs like a flange, along the periphery of which or along a particular PCD, some equally spaced holes are there. 6 holes, 8 holes, 10 or 12, 16, 24. So in that case, if you divide it symmetrically, either along X or along Y, you will find one part is just a mirror image of the other part. So in that case, if you identify the coordinates of, suppose 12 holes are there. So if you divide it into equal 2 halves, one will be mirror image of the other. So for one part, 1, 2, 3, 4, 5, 6 holes are there. So you have already calculated the coordinate of these 6 holes, and to get the coordinates of the remaining 6 holes, number from 7, 8, 9, 10, 11, 12, you need not to undertake any further calculation. Just change their signs. So you automatically get the coordinate points of the remaining 6 holes. So this feature is called, afterwards we will discuss, mirror imaging. So mirror imaging is basically duplication of one part to get the another part, which is identical with the former. So that reduces our programming effort. And another relative merits and demerits depends on in which way your coordinates or dimensions are given in the drawing. What is your source of part creation of the part programming? Will be given the component drawing. So in the component drawing, your dimensions will be given. So in which mode dimensions are provided? Quite often, if there are number of holes, just like your plug point, 2 holes are there, or there may be more number of holes. So you can provide the dimension distance between the holes, either from the origin or from relative measure. So in which way it is provided in your drawing, accordingly you can fetch the data directly from the drawing without undertaking much calculations. Okay, so accordingly you can opt for either absolute or incremental mode of programming. And to enable absolute or incremental mode of programming, there are 2 different G codes which I was talking about. In this case it is G90, capital G90, in this case G91. Okay, but no need to remember at this stage. During programming you will be accustomed with the different such codes. Just for example, I have taken this one origin, is a AutoCAD drawing. I have considered point number 1, point 2, point 3. These white color dimensions are absolute and yellow color dimensions are in incremental. You can it is clearly visible. Just consider the point. What is the x value of point number 1? 20. In this case, how much? 28. So what is the incremental? 8. And regarding y, you see it is 47. Here it is 12. It is going down, negative direction. That is so 47, 12. So 12 minus 47 minus 35. So this sign also you have to take into consideration. Otherwise there will be error. Okay. So this is how it can be solved. Finally, open loop. I will better explain with respect to the two drawings. That is the most important. This is the block diagram of the open loop control system, and this is the block diagram of the closed loop control system. But this closed loop control system is extensively used in the all industrial versions of the machines. You cannot achieve very fine accuracy in case of open loop control. But just to start with, how the system works? First, we require a drive motor. Okay. In case of open loop control system, your motor is stepping motor or stepper motor. Okay. So stepper motor works on discrete pulses. So if one pulse is issued, your rotor will rotate by some angular displacement. Usually 1.8 degree. Usually 200 gyrations are there. Just imagine your wristwatch and how your limbs are moving. One tick, some amount, one tick and some movement. So this is how. That means one pulse 1.8 degree, another pulse another 1.8 degree. So if there is a continuous series of pulse, so it will move continuously. So that is the principle of operation of stepper motor. Now usually the motor's rotational speed is very high. So for mechanical purpose, it is imperative or it is essential to reduce it by some magnitude, for which the very prominent or conventional common device is item is gearbox. So by incorporating a reduction gearbox, you can reduce the speed. If it is the motor is rotating at 900 rpm, if there is a speed reduction gear of 3, then the connected leads to will be rotating at 900 by 3. That means at 300 rpm. So speed is reduced from 900 to 300 by incorporating a gear train having reduction step or gear ratio 3. Okay, if it is 4, then it will be different. So our objective is that leads 2 is supposed to rotating at a lower speed. Now on the leads 2 nut is mounted, and on the nut work table is mounted. So the leads 2 is also undergoing rotary motion. Simply just imagine a nut, a bolt. If you rotate a nut or if you rotate a bolt, so there will be a linear movement. So rotary movement is transmitted to linear movement. So that is what exactly is our objective. Rotary motion of the leads 2 will be converted to linear motion of the work table and hence the job. If the job is mounted on the table, so automatically job will also have a linear motion. And one rotation of the leads 2 will ensure how much linear displacement from mechanical point of view. If I rotate a screw by one full turn, what will be the linear movement? It is equal to how much? Pitch or lead of the screw. So that is the linear measurement. So depending on the number of rotation per minute, we can have what is our desired level of linear travel velocity. But as the name suggests, you see, there is no, as such there is no loop, it is open. No feedback is there. That is why it is called open loop. So in regard to any discrepancy in the position or in the velocity, there is no provision for monitoring and hence no corrective actions can be taken. And another deficiency or the disadvantage of the stepping motor is that during metal cutting, high load torque has to be encountered. Okay, if the load torque is sufficiently high, then there is a possibility that stepping motor may lose its step. Okay, so high load torque transfer is rather difficult. So for lighter operations, or particularly for the toys, Chinese toys which are available in the for the child. So those are say small robot or small car, okay, in the form of toys. Those employ stepper motors, or some models you can develop in your lab. Those are usually good provision or application for using stepper motor. In contrast, a closed loop control system is much more complicated and sophisticated also. Here there is a little bit difference. You see, as far as the drive system is concerned, the stepper motor is replaced by DC servo motor. Okay, DC servo motor is based on analog signal. Okay. So first, the information which is available in the data processing unit, recall that particular block diagram. I told the high level language will be converted to machine language, which is in the digital form, 0-1, that is a digital form. So all the data processing takes place in the digital mode, but DC servo motor operates on analog signal. So digital signal has to be converted to analog signal, that means continuous. That is why one DAC, that is digital to analog converter, has to be installed. Okay, that is another feature. Second thing, that is the comparator. Comparator is also digital electronic device where there are two counters. Earlier I had given one example. You are supposed to move by 50 meter, that is your reference, and you start moving by 1 meter, 2 meter, 3 meter likewise. So 50 meter, which is your reference, that will be stored in the positive counter. Okay, and as you start moving, what is the actual, that will be monitored here by the position sensors. You see, this much portion remains same. That means this mechanical portion remains same. Only thing, stepper motor is replaced by the DC servo motor, and one digital to analog converter is there for conversion. And for continuous monitoring and taking corrective actions, one comparator is there. And it has got plus counter, minus counter. So signal which is captured by the position sensor, that is fed back to the negative counter for comparison. So the example that I had given you, 50 minus 1, this comparison equal to 49, 50 minus 2, 48. So this comparison, that means 48 millimeter is still to go to reach your destination. So this calculation will be continuously taken care of and implemented in the closed loop control system, so that eventually you reach your target destination with the desired velocity and of course to the your final destination. It is a simplified form. And last figure, this is the last one perhaps, as far as the diagram is concerned. This is actually called servo control loop. Now I have incorporated terms servo motor, servo control. Servo, what does it mean? Usual DC motor or AC motor, if you apply voltage, it will keep on rotating according to your desired speed. But for precise position, angular position control, this servo is used. What is essentially what it is? The system, the motor combines or includes your feedback system together. That means depending on the feedback that is coming out, accordingly fine precise angular motion control is possible. So since our objective is to ensure higher level of accuracy, that is why, and that is also based on the feedback signal. This much it is rotated, still this much is is still left. So sensing and acting. So that is what exactly is the meaning of servo. You sense and act. Okay. So the true servo control loop, you see that there are two loops. In the block diagram I had told there are, one is velocity measurement, another was position measurement. So for velocity measurement, one inner loop is there, and for position measurement there is another outer loop is there. You see, again this is a position comparator, digital to analog signal. One additional element is incorporated, that is amplifier. Okay, to boost the voltage, which is essential to overcome the cutting force and torque, the voltage to be boosted up, that is amplified. That is why one amplifier is incorporated here. And this comparator is for velocity, because we require both. just go for your simple mechanics. What is the displacement relationship with the velocity and time? X equal to Vt, that means displacement equal to velocity into time. So velocity is the most fundamental. Based on your velocity at a given time, how much distance you will be able to cover. So if you follow by 5 meter per minute, then in 2 seconds it will be 5 meter per minute. Of course, it has to be converted to second and multiplied by 2, so that you can get the equivalent amount of displacement. So your displacement depends on the velocity. That is why velocity is an inner loop and position as your outer loop. Okay, this part I have not elaborated. So this servo motor, gearbox, machine tool, and these two are basically two different types of transducer or sensors. This is for velocity measurement, that is which I had called tacho generator is the preferred one, and in case of position, it may be encoder or it may be your linear scale. Okay. So the input signal is stored in the positive counter of the comparator. Okay. The digital signal is converted to analog signal to drive the motor. This signal needs to be amplified before input to the motor. A servo motor, it may be DC or AC. Earlier days it was predominantly DC, but now all DC machines or DC motors are replaced by the AC. Their performance is quite good, highly reliable, and almost maintenance free. That is used for precise control of angular position, velocity, and acceleration. The system comprises a suitable motor coupled with a sensor for position feedback. So servo motor means the drive system along with the feedback and the sensory information, so that it can sense and act according to the program or according to the requirement. Actual slide displacement, that is the position, is sensed by the encoder, as I told, and sent to the counter of the comparator for comparison with the reference signal. So what is in the program? Suppose just for an example, say your movement in a lathe along the z axis while undertaking a turning, suppose G01 Z minus 50 F.2. This is a program value. So this interprets that along the Z minus direction, the tool should supposed to move by 50 millimeter, maintaining the speed of 0.2 millimeter per revolution. Now it is required that during implementation it has to be monitored continuously, so that eventually this 50 millimeter displacement is achieved, and while moving so it would maintain the defined velocity or the speed of 0.2 millimeter per revolution. So there are two parameters, one is displacement Z minus 50 and another is velocity feet, which is expressed in millimeter per revolution. If you multiply it by RPM, you will get in millimeter per minute. So velocity has to be measured along with position. So both needs to be two different parameters to be measured by the two different category of sensors. So in generically we call error signal equal to reference signal minus actual signal. So during this particular example, your reference signal will be 50 millimeter, and once it starts moving 1.5, 1.75, of course it will be much finer. Okay. So continuously your actual position keeps on changing. So if actual position keeps on changing, so error signal will also keep on changing. Okay. So this error signal, that is the remaining part, that will be actually utilized for generating commands to the servo motor, so that it keeps on rotating unless and until when actual signal and error reference signal will both become same, 50 minus 50, 0. So no further movement is required, then error signal will become 0 and machine stop working. That means that particular program block of information is executed. Clear? Just one more slide. So this error signal is generated continuously to drive the motor until the program's right position is reached, when error becomes 0. Two loops are there. The inner loop is for velocity control, which uses tacho generator as velocity sensor, and outer loop is used for position control, which utilizes shaft encoder as position sensor. Regarding this tacho generator and encoder, we will discuss towards the end, okay, about the different types of sensors we used in the CNC system. So NC CNC system, position means displacement and velocity means speed. These two term or relationship is very important from our metal cutting point of view. Although generically we call it as a velocity, but in our manufacturing or metal cutting fraternity, it is speed, and position means displacement. So discrepancies in the side movement and velocities can be eliminated by two closed control loops so as to get rid of any error. So eventually we will get perfect achievement or accomplishment of our desired movement of 50 millimeter, whatever may be the program value, and of course following the definite velocity of 0.2 millimeter per revolution, which is incorporated in your program. Okay, so that is the essence of your servo control loop. So that's all about the today's lecture. So we had covered up the axis nomenclature, this positioning system basis for classification, point to point, contouring, continuous, linear, circular, cubic. These are one part. Method of programming based on the absolute mode or incremental mode, and this closed loop control approach and open loop control approach. Okay, so majority of the numerical problems are based on this open loop control system and closed loop control system block diagram. Okay, so you be very careful and you should understand its operation is very simple, and majority of the problems which appears in your gate all are majority based on open loop and closed loop control system. Of course, some added analysis are required before we venture out for the problem solving. So those we will be including in our next, maybe my lecture number 5 or 6.